Hello, and thank you all for joining this first webinar on the electronic assembly adhesive solutions for the next generation printed circuits and sensors. My name is Donovan Cerneüs. I will be presenting the electrical based version of this webinar. Next to me is Tony Winster from Henkel, and he will be discussing the assembly films solutions from Henkel. If you happen to have any, if you happen to have any questions during the webinar, there is a questions tab in the GoToWebinar, and we would kindly request you to fill in your questions there, and we will try to answer them at the end of this webinar. So as I already said, I will be discussing the assembly adhesives, both the electrically conductive ones and also the electrically non-conductive ones, and Tony will take over for the film section. But before we dive deep into the assembly adhesives, I quickly want to take this moment to share some information on Kaplink. Hopefully a lot of you guys already know what Kaplink is and what we do, because we are the channel partner for Henkel. And I specifically say channel partner and not a distributor, because we try to do more than just ship boxes from location A to location B. We have a special semiconductor focus, and we have trained engineers across the world to help our customers and also the customers from Henkel to support their projects and processes. To dive specifically into the Kaplink product portfolio we represent from Henkel, that would be the die-attach materials, the encapsulants and underfills, for instance, cloth tops and demi fills. And for this webinar, we will be discussing another product category we represent from Henkel, and that is the assembly adhesives, and of course also the assembly films. But first, let's start. What are assembly adhesives? On a really basic level, assembly adhesives are used to mount electronic components to a printed circuit board. This could be either a passive component or bare dies, and this could be also on flexible circuits or for sensor applications, and also for a wide variety of applications. Think about solar applications, maybe automotive applications, consumer electronics. There's a wide variety of applications where these materials actually could be used and are used nowadays. If we look at a really basic level of the three main constituents of all adhesives, or more specifically these assembly adhesives, you can categorize them in three main categories. So it is a thermoset material, which means that it's based out of a resin. And this could be anything from an epoxy, a silicone, an acrylate, or a mixture of multiple resin types, which we call hybrids. These resins need a hardener, or also known as a catalyst, to basically kick off the reaction, also make sure that the reaction is moving forward as well. Some hardeners examples are peroxides, amines, imidazoles, etc. The final constituent is actually the filler type. So for the electrically conductive adhesives, this filler type would be a filler that could conduct electricity, mostly metals, so for instance silver, copper, or in some cases gold. And for the non-conductive adhesives, it would be mostly silica or some other non-conductive filler types like Teflon. If we look at the resins in specific, there's a multitude of different options. So really the workhorse in the industry would be the epoxies. Epoxies have some advantages and also some disadvantages. And some of the advantages would be that epoxies are good on a variety of substrates. They have really high adhesion strength to multiple substrates. There's a lot of formulation variability possible with epoxies. One limitation, however, is generally speaking, they have a longer curing schedule. Another option would be an acrylate. An acrylate can cure really fast. There's flexibility from rigid systems and also flexible systems. But the drawback from acrylates is that because there's a radical curing mechanism going on, it could be inhibited by the biradical oxygen. And there's also limited thermal stability for acrylates. Another option would be silicones, because they are highly flexible and they have good high temperature stability, but they have a relatively low adhesion strength, and they also have a permeable structure. You could also mix multiple resin types together to get the best benefits of the different chemistries. But the unfortunate drawback is that you also have some of the negative portions of the different chemistries. So generally speaking, the adhesion for hybrid materials is also lower than, for instance, epoxy type. If we dive a bit deeper into the hardeners, there's a wide variety of hardeners that could be used into the formulation, but the target and main goal of a hardener is to basically start off the reaction and make sure that the polymerization reaction starts going. A wide variety of materials could be used, and they have an impact on the eventual properties of your adhesives, but it is a very complex topic, and it's also difficult not to share a lot of proprietary information, but a lot of these hardeners can also be found in the SDS, which is shared on our website. If we dive into the fillers, we separate them in the electrically conductive and also in the electrically non-conductive portion of the filler types. So the electrically conductive ones, you can even divide them into the amount of electricity they can conduct. So carbon would be a lower conducting material, copper would be medium, nickel would also be medium. The best one or the highest one would be silver, also because of the oxidized form of silver. So silver oxide is still conductive, while this for other metals, this is not necessarily the case. And the most reliable electrically conductive material is gold, but gold has the drawback that it's very costly. For the non-electrically conductive filler types that you could use, the most common one is definitely silica. And these fillers are actually used for instance, CTE control, but also for the viscosity or thixotropy of your materials. If you want a somewhat higher thermal conductivity of your non-conductive adhesive, you could use, for instance, aluminum nitride or boron nitride. And if you want some toughness in your formulation, you could add, for instance, Teflon. If we dive a bit deeper into the ECAs and in the what, why, and wheres, on a really basic level, an electrically conductive adhesive is a metal-filled paste with the ability to conduct a current. But why would you actually want to use it? Why? Because you want a component to have a certain functionality on your printed circuit board. So the where is then logical. You want to use the material to mount components to your printed circuit boards or other substrates. If we talk specifically about the conductive fillers and the possibilities of these conductive fillers, it is generally speaking a really highly filled material. So 75% up to 85%. This is done because we want to have an entire cluster being formed during curing. So initially, when the material starts curing, small clusters are formed, and because of the high content of material, eventually a so-called spanning cluster is formed. So you have a consistent electrical conductivity from your component to the board, and it will be the same for every time you cure the material. Most materials we will be discussing today and also in the Henkel portfolio are the so-called isotropic materials. Isotropic simply means that it could conduct electricity in all directions. So X, Y, and Z, it doesn't matter. Another option for a material is an anisotropic conductivity. This simply means that there's only conductivity in the Z direction. Henkel has one product in particular that could be used for certain applications, which would be the ACP3122. Applications where this material could be used are, for instance, passports, smart cards, or in RFID applications. But why would you want to use electrically conductive adhesives? Well, there's four main reasons. So there's cost reduction, there is green technology, there's an improved reliability, and there's miniaturization of your package or 3D integration. So generally speaking, these ECAs have a lower temperature cure. so your overall energy consumption in your process would be lower, which could be a cost benefit. Additionally, because the material can cure at a lower temperature, and in some cases even as low as room temperature, some critical components, some heat-sensitive components won't be impacted when you actually use the ECA for that specific application. The ECA also has some very high operating temperature reliability, which could be beneficial for a multitude of applications. If we want to compare ECAs to one very common industry workhorse, it's solder. And both of them have benefits and drawbacks, and I want to highlight actually the benefits of both material types. So solder, pound for pound, is cheaper than ECAs. It is also really easy to actually rework because there is a certain temperature where it goes from a solid into a liquid and then back to a solid. If you go below the temperature, there is self-alignment of your components. Solder is very well established into the market, and it has comparable electrical properties compared to ECAs as well. ECAs, however, they have a no lead substitution for thin lead solders. The curing is accomplished at way lower temperatures compared to solder. There's the possibility for isotropically and also anisotropically conductive adhesives. And the ECAs can meet really high automotive standard reliability requirements. And main benefit also from ECAs is there's no flux residues. So there's no cleaning step associated with using ECAs, which could be a benefit. And one special option for ECAs is also the hybrid silver sintering materials, which could have a better thermal conductivity and also better electrical conductivity compared to standard solder materials. If we dive a bit deeper into the product specifically, we can differentiate the electrically conductive adhesives into multiple categories. So we first divide them into either component attach or inlet attach. And if we divide the component attach even further, we can divide them into noble and non-noble, and then even further into rigid and flexible. And flexible, you are probably all very aware of the term modulus. So there are different modulus. So there's young modulus, storage modulus, tensile modulus. For this webinar, we won't dive deep into that topic, but just as some basic knowledge, the modulus describes the tendency of a material to deform under a certain stress or force when it's applied to it, and that is calculated or given in either megapascals or gigapascals. For a standard, what we call rigid material, we will be thinking about certain epoxy materials. Then we would say that the modulus of the material, generally speaking, is higher than 1000 megapascals. But for more flexible materials, for instance, silicone materials, we would be looking at a modulus which is lower, or in some cases, way lower than 1000 megapascals. The modulus is measured with analysis called dynamic mechanical analysis, which can, generally speaking, is given on a lot of TDSs for all of these materials. If we dive deeper into some more product-specific applications, I want to highlight these products, so the 3103 WLV and also the 3104 WLX. Those are both epoxy-based materials, silver-filled, and they are rigid. These ones specifically are compatible with a non-noble substrate. So for instance, a tin substrate, and they have the ability to cure at a relatively low temperature, but they can also cure during a reflow cycle, which could be beneficial into certain applications. The differentiation between the 3103 WLV and the 3104 WLXL is really the way it either is beneficial for dispensing or for screen printing applications. If we look into a certain application where the 3103 WLV could be used, is a grounding application, for instance, for a lens barrel to lens housing attach, or a lens barrel housing to a PCB attach, or even for a lens barrel to a camera module housing. So what would be the main requirements of these materials? Well, you want a good sealing, you want a stable volume control as well, you want a low temperature but fast curing material, you want a high adhesion to a multitude of different substrates, you want a good operating window between, for instance, -40 and 130 degrees, you want some good stable electrical connection as well, and the best option, generally speaking, is a silver filled material. However, the silver filled material is also the most expensive option of the bunch. Another option could be a silver plated copper material. This would lower the electrical conductivity of the material, but it's also a bit lower in price. A different option could also be nickel, which is the cheapest of the bunch, but there's also some health and safety concerns with using nickel, as it's toxic for humans. I also want to highlight two new products, so the ICP 2120 and the ABP 2034. Both of these products are actually already being used in high volume in Asia, but both of them are also now under review for introducing both in Europe and also in the Americas. So these are the products worth to watch. So these products, the 2120 is an MS polymer, which is a silicone-free material that actually has some of the properties that a silicone would offer. So a low modulus material and some more flexibility. Or the 2034, which is a hybrid material, which can also cure at lower temperatures and also has the lowest volume resistivity. We will share a handout of this webinar with every attendee afterwards, and that's why we also want to have some product selection guides in this webinar. So I won't go into detail into this slide, but when you go back and you want to watch this or read through it in a PDF document, then every information you need is visible on these slides. If we dive into some more flexible materials, so all of these materials are actually silicone, and these are specifically designed to attach to noble substrates. We're talking about the ICP 4000 series. So there's a multitude of applications where these materials could actually be used. And the differentiation between the ICP types is the highest conductivity one, which would be the 4000 version, the most all-round version, which would be the 4001 version, or the lowest curing temperature product, which would be the 4015. Then we want to discuss a product which is the 84-1 LMI. I think a lot of people would actually know this product because this is the industry workhorse die attach material. But this material has some great aspects and some benefits. So it's highly reliable. It could pass various outgassing standards from NASA, and it has a good electrical and thermal conductivity. If we highlight the three main products, it would be just the standard 84-1 LMI, also the LMI T1, and also the SR4 option. But I hear you all asking, what is actually the difference between all of these chemistries? Well, the S stands for a low viscosity version, and the SR4 is for a high-speed dispensing option. The T and the T1 are the higher thermal conductivity options. The NB would be the no bleed option or lower bleed option. And then there's also the 84-3, which would be the same chemistry type material, but it would be the non-conductive version of the 84-1. The 84-1 LMI can be used also in a screen printing setup. So if we compare the 84-1 LMI together with some other product, which I previously discussed, the 3104 WXL, both can be used to screen print really small dots with a diameter of as thin as 80 micrometers, which could be used, for instance, in micro LED applications. Another really low modulus material I want to highlight is the CA3556HF. It has a low modulus of only 650 megapascals at room temperature, which is generally speaking a more flexible material. And because of the flexible nature of this material, it is actually also being used in flexible circuits and other grounding applications where the product was not originally designed to be used. Once again, product overview of the noble metallization products that could be used. I will skip this for now, but once again, you can check this later after the webinar. Let's move on to the non-conductive adhesives. What, why, and where? Well, what? It's an adhesive, of course, to bond components in a non-conductive, more structural way. Why do you want it? Well, you want some flexibility, maybe some lower modulus. You want some strong adhesion. Maybe you want some electrically insulating material for your components, or you want to have some thermal conductivity properties, or you just want to increase the overall reliability of your package. Where would you use these materials? Well, this could also be a multitude of different applications, but for instance, camera modules as well, some different sensors, and also low temperature curing possibilities. A quick overview of the heat curing non-conductive adhesives Henkel and also Kaplink can offer to the market. I want to highlight is definitely the TE3530, which can have a thermal conductivity of more than 2.3 watts per millikelvin. And also the possibility for dual curing non-conductive adhesives. So these materials first have a UV cure and afterwards have a temperature cure. The reason why this is done is to have the quick alignment or the self-alignment of materials, and then do a heat temperature cure to actually achieve the higher reliability aspects of certain applications. This can be used in, for instance, optical switch precision alignment or in some certain sensor applications. So what would be the benefits and drawbacks of using a UV cure? Well, the strength is definitely that it's, generally speaking, one component. It has a very fast cure at room temperature. There's less equipment needed to actually use a UV curing material, but there's also some limitations. For instance, a UV cure is a radical curing mechanism, so oxygen inhibition is always a concern. There is a certain line of sight cure problem potentially, where the material isn't cured properly because the material or the light did not reach that spot. It could also cure under ambient light temperatures, which could be a problem. So there are still a lot of limitations with using UV curing materials. I want to highlight some materials that can indeed do the dual curing mechanism. So there's a variety of materials, acrylates, but also epoxy materials or certain hybrid materials. So epoxy and acrylate as well. So thank you all for your time and for being here. I want to give a special thanks to George, who helped me to put down this presentation. And I also want to thank a lot of Henkel colleagues, so namely Ruud de Wit, Tony, who's my co-host today, and Jan Wijgaerts as well, and Lyle Canteleo, my colleague, who helped me with making all these cool images. Thank you all, and I will hand it over now to Tony.
Okay, thanks, Donovan. All good stuff, very interesting, and good afternoon, everyone. Oh, good morning, if depending where you are in the world. So I've been asked to present a few slides talking about assembly film adhesives, which for some applications offer a quite attractive alternative to using a paste. If we go on to the next slide, we can begin to talk about what they are and where they could be used. And the reason to use a film in electronic assembly is because of problems and limitations. And this highlights the issues really. On the left-hand side there, you can see a fairly large area bond that has to be made. All that glue has been dispensed. It's an awkward pattern to dispense, and it's awkward when you place the component on there to get all the air out of the bond line. You can see on the right side an X-ray or acoustic microscope image showing that there's a lot of voids in that bond line, which may or may not be a problem, but most people would see that image and not be very happy with it. So if we go on to the next one, where would you use such films in a bit more detail? Well, specifically with large areas really, where it's important to get a uniform distribution of adhesive over that large area, and also to control the bond line thickness, consistent around the bond line, but also from one part to another. And that with a film is controlled by the thickness of the film. So really you're pushing that quality control back to the supplier rather than having to do it yourself. It's also particularly useful if you've got complex patterns where it's difficult to get a dispensing pattern that will give a controlled uniform fillet around the part. Maybe you could do that with screen or stencil printing. That's one solution. But if you're using a package or a substrate with a recess or a pocket in it, that's quite difficult to achieve, whereas with a film, it's very easy to achieve. And the final bullet point on there is that some of these more modern films have got quite respectable electrical and thermal conductivity, so they're beginning to be used for power and high frequency type applications. So on to the next one. So here you can see that the high thermal conductivity films would have bulk thermal conductivity up to about 7 watts per meter per Kelvin, which is much higher than you get with thermal tapes or whatever, which would be around 2 watts per meter per Kelvin maximum. And they combine that with a high mechanical strength. These are thermosetting materials, so they've got adhesion strengths comparable or maybe even higher than pastes, with lap shear testing around about 20 newtons per square millimeter. And that compares with pressure sensitive tapes, which would be less than 1 newton per square millimeter really in a tensile lap shear. So in terms of robustness and reliability, they are really, really attractive. Okay, so next one. Comparing pros and cons with different competing technologies for using a film adhesive. So if you compare them with a paste adhesive, which is the first thought, I guess, is that films are easier to process for large areas. And although the pricing seems to be higher at first glance, the overall total cost of ownership can be better, especially when you consider things like device yield, scrap rates, that type of thing. If you compare it with solder, well, typically the curing temperature of these things is about 150, so it's lower than solder. You're building less stress into the module. And they're also more flexible and more crack resistant than solder, typically anyway. And if you compare it with a pressure sensitive adhesive, these thermosetting films are much stronger, and they'll give a much better performance and reliability than just a basic tape, pressure sensitive tape. All right, next one. So there's a few sort of application sketches here. There's a good old-fashioned hybrid circuit with a ceramic board glued down onto the base of a metal package with an epoxy film preform. And I think you can see that immediately that the film would cope better with the warpage on the ceramic and on the package base compared with a paste. It will give a uniform bond line thickness. But typical applications would be power amplifiers, various electronic devices, usually in a high reliability environment, so military, aerospace type applications. Avionics certainly, sensors, guidance systems and radars, and as I said earlier, increasingly for power modules used in aerospace, defense type applications. Okay, next one. And again, a few pictures showing use in high frequency applications, both military radar systems, but also increasingly in wireless telecom base stations, where boards are being bonded onto metal backplanes. And those can be sizes up to about 6 by 4 inches, 150 by 100 millimeters, and giving perfectly adequate reliability. Okay, next one. And in addition, well, there's other sort of miscellaneous and niche applications. One of them might be a MEMS die attach, where it's very important to control the properties of the bond line. So the bond line thickness in particular and the spread of the glue around the package is very important to control that, to control the sensor output, and increasingly high reliability applications as an alternative to solder. Okay, next one. And we can say a few things about the film technology, and I think it's important to state that these films are not so very different chemically from the pastes that Donovan's given a very good description of, and they consist basically of a resin hardener, so it's a thermosetting system, with a filler in some cases. So that filler could be usually silver, although there are some gold products for very high value niche applications. Or if not so high thermal conductivity is needed, or some electrical insulation, the fillers could be silica or alumina. And in some cases, there's products with no filler at all. They're just resin hardener and maybe a carrier. But essentially, they're very similar to the pastes, except that they're formulated with resins that are higher molecular weight than the paste, so that they're solids at room temperature, and that way we can fabricate them into a solid film. Okay, next one. And here's a few words about support carriers. That traditionally the more established films were fabricated on a glass fiber carrier, where essentially the resin hardener filler solution was dipped into a sheet of fiberglass fabric, pulled out under very controlled conditions and dried, so that the fiberglass carrier is embedded within the film and it'll just stay there forever. And the same process could be used with a plastic film. Dip a plastic film into the solution, such as Kapton, and that way you get a film which is a very, very good insulator, the Kapton, but it's coated with a very uniform layer of thermoplastic glue on either side of the Kapton. Or more recently, what we've learned to do and what customers have demanded really is to fabricate unsupported films, where we'll coat the film solution onto one side of a release liner, basically a roll of plastic, and dry that, and that way the material can be shipped with the release liner in place, and then the customer removes the release liner to give a completely unsupported film, so there's no barrier then to electrical or thermal conductivity. So there's a variety there. So we've got different formulations and we've got different formats. So already the product range, the product portfolio is beginning to look rather complex. Okay, on to the next one. And the formats that we would normally supply typically would be in sheet format, a few inches square the customer can specify, but typical standard sizes would be a 10 by 12 sheet, 25 by 30 centimeters, Oh, back one. Back. That's it. Brilliant, thanks. And also we can fabricate at different thicknesses, which could be in the range typically 50 to 150 micron, depending on the formulation. And then the customer can select within this range, typically with a tolerance of plus minus 25 micron. I'm not saying every combination and every permutation is available, but at least from a manufacturing point of view, that's what is technically possible. All right, next one. Now, as we mentioned, complex shapes is one of the attractions of using these film adhesives, and so they can be cut, the sheets can be cut into fairly complex shapes, pre-cuts, either by the customer or by Henkel. So if we look at the next one, different ways of doing that, either with a simple knife. The simplest way would be to do it by hand with a knife and a ruler, but knife plotters are available. For small runs, or if we expect a lot of design changes, laser cutting is a possibility, which we've got in our California facility, or for higher volumes, we need a quick throughput, and it's worth investing in a mechanical punch system. Then a punch and die is overall the most economic. So all those different options are available. Okay. And a few words about processing is that the parts that you're bonding together may look flat, but they're not flat. The film itself is solid at room temperature, so you need to do something to make it wet out into the grooves, into the roughness of the components. And the way to do that is to warm up the resin a little bit, warm up the film, to soften it and to apply some pressure. And a combination of heat and pressure, we can advise on that, but usually it needs a bit of DOE work to optimize that process. So if we look at the next one, there's some data here with one specific film. You can see bottom left there, as you, or at low temperature, the film is very high viscosity, and as you warm it, the viscosity drops as the resin begins to melt, gets softer and softer, and eventually it reaches a temperature where it's beginning to cure and the viscosity goes back up again. So to combine that, or to build that into an assembly process, you need to warm the glue up gradually to allow it some time to wet out onto the surfaces before it fully cures, and then leave it for the curing cross-linking reaction to complete after the wet out phase. So, and typically the curing of these things is, like I said, an hour at 150, although there are some different formulations that will cure at lower or higher temperatures. Okay, on to the next one. How much pressure to apply during cure? We always recommend, for best performance, to apply some pressure during cure. It's, for some applications, is not strictly necessary, but you'll get the best performance, best reliability if that pressure is applied. And you can see here that different formulations have different amounts of flow. They use different resin systems. Obviously, the pressure would need to be tailored to the bond line surface area, and the combination of those two, the formulation of the glue and the bond line area, will lead empirically to a points rating, and that will give a starting point for the pressure that's optimum during cure. So on to the next one. Some quick pictures here of the sorts of ways that that pressure can be applied. One's with a simple press, heated press. Very, very simple if you've got a simple configuration of component. On the next one, you could use spring clamps, very, very simple but effective system. You could use weights, takes a bit of time to warm them up during cure, so if you take that into account. But if they're designed properly, they'll apply a very, very uniform pressure, especially if you've got conformal layers built into there as well to even out the pressure. And on to the next one. Another way is to use a vacuum bag, build the parts up, put them into a vacuum bag and suck a vacuum, so you can get up to one atmosphere pressure. It's not very high, but it's very, very uniformly applied and cure within the vacuum bag. Or on the next one, if you really want to over-engineer it in many ways, you could put that vacuum bag into an autoclave and increase the pressure, the isostatic pressure on the parts during cure. You're beginning to look at capital investment here with autoclaves and whatever, but some companies have this type of thing. And the final thing, the final option on the next slide would be to, if the parts are flat, relatively flat, would be to use a programmable heated vacuum press, so that you can program this to apply pressure, well, initially vacuum pressure, but then to apply the heat and compression during the cure. And people do that. There's many thousands, millions of parts maybe been built with that sort of system. So that's an option also. Okay, next one. So everything that I've said suggests pressure during cure, but actually what it's good to do is to wet out the parts or tack them down into place, so that you make a sort of a temporary bond, get the wet out done at 40, 50, 60, 70 Celsius, in that range. Stick the parts together onto that melted resin, but don't cure it. And that way you can transport the parts around. They've got plenty of adhesion to be handled. And then maybe you need to also apply pressure during cure. And maybe you don't, actually, depending on the application requirements. But you can see there that a bit of heat and pressure on the photographs indicates that that does really improve the wet out of the parts rather than assembling them cold. Okay, next one. Just one slide here about the mechanical properties. Normally with the paste adhesives that Donovan was talking about, we would measure adhesion with a dye shear test. That's not really appropriate for film. So we use a lap shear test where we bond two aluminium strips together, cure them under pressure, and then pull them apart. So it's a fairly large area, relatively large area bond. It's an industry standard adhesion test, and so long as it gives a cohesive failure, which it usually does, then it doesn't matter the fact that the parts are made of aluminium rather than one of the typical electronic materials that they would be used in conjunction with. Okay, next one. Sometimes parts would need to be exposed to solid reflow after they've been assembled, and as I say, there's different film formulations, and some of them are better than others at withstanding high temperature exposure, and there's a list here of which products are the most or the least robust, so that can be studied later. Okay, next one. And here we're getting on to the portfolio, because I've painted a picture, I think, that there's many different formulations and different sort of applications, and to try and bring some simplicity out of it. You can see here that there's on the left the electrically conductive materials, thermally conductive that would have some mineral filler, and the materials without any filler on the right hand side. So we've also highlighted there some of the parts are, or some of the formulations certified to MIL standard 883, test method 5011, so they're certified for American defense applications. And we've also highlighted there the difference between, or highlighted which films are supported and which are unsupported. So you can begin to pick and choose the most appropriate film for the application. On to the next one. And this is almost a selector guide of the same information, but in a different form. So looking at the different electrically conductive films, you can see that typically they cure at 150, although there's the ECF 568 there that will cure at 95. They do have different thermal conductivities and volume resistivities, and they also have different mechanical properties, so they would be suitable for different application or different design modules. And I think on the next slide there's a list of the non-electrically conductive ones. So typically the products with a K after the name would have a mineral filler to try and boost, well not try, but to boost the thermal conductivity up to about 0.7, approaching 1 watt per meter per Kelvin. And the unfilled materials would have a thermal conductivity typically of 0.2, which is what you'd expect for an unfilled resin. But they do have very good insulation resistance properties. So on to the next one. I think that's what we have to say about films. I hope that's it's a very quick introduction. And what I would say is that in summary, really, that portfolio is quite complex. But one of the benefits of this sort of presentation webinar is that at least you know where to find us, to find someone to discuss and give advice on which products are the most suitable for any potential new application. Okay, that's me done. So hand over to Donovan for a conclusion.
Yes, thank you, Tony. Thank you very much for your interesting talk on the assembly films. I think we can actually go over to some questions, if there's any questions. So towards the Q&A session. Let's see if there's something coming in. Feel free to ask any questions, whatever comes to mind. Just type it into the questions box in the GoToWebinar, and I see a question. The question is, why is nickel preferred for an ACP? So an anisotropic conductive paste. Maybe you can take that one, Tony, because you're the technical.
I can say a few words about it. Actually, it's not nickel. Usually we use gold-plated nickel to give it some stability with time. But nickel is quite good because it's hard. Gold is soft and it just squashes. So it's good to make the particles out of a fairly hard material, and you can push the components down and make a good contact without distorting and flattening out the small particles.
Okay, thank you very much, Tony.
Okay.
I hope that answered your question. Any other questions still pending? Could you comment on the repairability of ACAs versus solder materials? Okay, that is a good question. So I think the well, reworkability of the ECAs is more difficult because it's a thermoset material. So for solder materials, you're really looking at well, a melting temperature where it actually goes to liquid and then to solid. So it's easily reworkable. But for the ECA materials, you would have to remove the entire bond because you're going to a thermoset material. So the material just turns hard and it doesn't turn to liquid anymore. Any comments or anything to add, Tony, to that?
Well, I agree with you. I mean, it's not as easy as with solder, but it is done, and particularly with these complicated, expensive modules, if those are assembled and you find that there's one defective component on there, it's well worth going to the effort of heating the whole thing up, removing the component, cleaning up, removing any debris that's around, and fitting a new component, and that's widely done in the industry. Yeah.
Okay, let's see if I can make it bigger. There's a big question coming in, but I will maybe pop it out so I can actually. For gluing down a high power electronic component and designing for reliability, how do you decide between a low CTE rigid adhesive or a higher CTE flexible adhesive? Well, I think the answer to that question is it's all application dependent, and the benefit of a more rigid system is it, generally speaking, also has a higher adhesion force, so it can more easily keep hold of the component. But the benefit of some of the, for instance, silicone materials, where you have a lot of flexibility and the ability to basically absorb stress under multiple temperature cycles, could be beneficial for certain applications. So it's really a application-dependent decision which material you would prefer one over the other. I hope that answered the question. Otherwise, Tony, maybe you can add something.
Just to add a few words on that, is that the modeling software that's available is getting better and better all the time, and the product characterization data from Henkel and all their competitors is getting better all the time. So it's possible now to make a much better estimate of how a module will perform with different types of adhesive than it was even 2 or 3 years ago. So that's one thing to say. It's often worth investing in some decent software and some decent people that understand how to interpret the results, which is not a trivial thing. But understand, I mean, we understand that that's not a trivial question, it's a perennial question, and in the end it's got to be established really by building parts and testing them. There's, even with the best modeling in the world, it's not really accurate enough or reliable enough to make a 100% guaranteed prediction of which is the best solution. Yeah, I think that's about all we can say, really.
Okay, thank you. And I see another question for you, Tony. Is the ACF material also easy to dice if it's applied on a wafer level?
The ACF, you mean a film?
It's the ACF material.
So what we've been talking about today is what we call assembly films, which are made as freestanding films. But there's also separate product range that's designed for wafer application, where the film can be laminated onto the back of a wafer and diced, so the chip can, or component can be picked up together with its glue and put down on a lead frame. So I think that's the subject for a separate webinar. But specifically answer the question, those wafer level films tend to be a lot thinner, lower thickness. They're typically 20 micron type thickness, whereas so they're relatively easy to dice through, whereas the assembly films we've been talking about are thicker than that, typically 100 micron. So dicing is more of an issue. I wouldn't say it's impossible, but it's a slow old process to dice through these.
Okay, thank you. And then I think we have one more question afterwards. We will wrap it up for today. Any ITAR issues or ITAR issues using your adhesive?
ITAR is a consideration, and it's something which the manufacturing plant in California is very, very conscious of, and has been designed around actually security of drawings and piece parts. So it's something that we're conscious of, something that we follow, but it's not normally an inhibition or a restriction on customers buying material for new component for new applications or new components. It mainly relates to the drawings of the preforms, which nobody would want to copy that, I don't think. If that answers the question.
Okay, I think that's it for today's webinar. We will have another session later this night. But I want to thank you all for attending the webinar. Thank you very much. And if you happen to have any additional questions, feel free to contact Kaplink. We are in direct contact with Henkel. So any questions that maybe are having some super high technical aptitude required, then we are in direct contact with Henkel and we can support you directly. Either at sales@kaplink.com, or you can use our standard info email at info@kaplink.com. I hope everyone enjoyed the webinar, and once again, thank you, Tony, for presenting the assembly films, and I think we will see you all for the next one.
Yeah, okay, thanks everyone. Yeah, bye-bye.